All right, Richard, you want to take it away again?
Yep. I'll carry on. Thanks a lot, folks. All right, I hope you've managed to get a nice good cup of tea, coffee, whatever you want. So we'll carry on now. What's going to move onto now was to talk a little bit about what we can do with the IPS data, more in the real world, as it were, to do with in a space weather context. So, if we have many observations taken over a whole solar rotation from any of the instruments, then it results in the sun's frame of reference in basically many overlapping lines of sight between the antennas and the radio sources. And that's what you can see in the top left image here, sort of depicted. And that allows us to use tomographic inversion techniques to effectively create 3D reconstructions of the solar wind in terms of velocity and in terms of G level, which we can then use as a proxy for density being enhanced or not. And there are a number of stations worldwide which are really necessary to try and continually monitor the solar wind to be able to do this. So the current dedicated observatories, the primary one is the ICE instrument in Japan, which is basically observing every single day throughout the year. The MEXART system in Mexico, which has been in existence for a few years, but they've had some difficulties. Now following a digital upgrade, they're now verging on becoming fully operational. You've got a system in Pushina in Russia, which is also basically observing every day, and the UT radio telescope, which was observing every day up until fairly recently, but I think right now it potentially isn't. And then you've got instruments such as LOFAR and the MWA who can take IPS data, but are not instruments dedicated to do so, at least not yet. But ideally, the more instruments and the more data we can combine in the tomographic image, the better that tomographic image can be. And so what we end up with is effectively plots like such as on the right-hand side here. So the 3D views of the velocity and density can be created throughout in the heliosphere. And what you see in the top right plot here is a reconstruction of solar wind G level taken from the ICE instrument in data from the ICE instrument in Japan. And this is a sort of sky plane view. So it's equivalent to the view of the LASCO field of view. And you can see the LASCO CME in the image on the left, and you can see the extension of it as it propagated through space in the plane of the sky, in the reconstructed IPS data on the right there. Looking within the ecliptic plane, we can see similar things here. So you can see again these denser structures streaming out, and the CME in this particular case, I think is there. Streaming potentially, it's not towards Earth, but anyway, streaming somewhere. And the Earth is given by this cross feature just here with a depiction of Earth orbit with a black circle. And these data from these reconstructions, we could take data from any point in these reconstructions, any point in space, any point in time, and then use that measurement, as it were, to compare directly with in situ spacecraft measurements. And that's given by the plot on the right here, where the solar wind density is given in the black line, measured by the wind instrument out at L1, and the dotted line here is the equivalent measurement coming out of the tomographic reconstruction from IPS data, given with the red dashed line. And you can see that in this particular instance, it provides a really very good match indeed. And in many cases, it does provide a pretty good match. Sometimes not quite so good, but most of the time it does pretty well.
Richard, how many observations do you have to, or like, what is the cadence of producing a map like this? How long do you have to observe?
Yeah, I mean, these are quite low resolution maps. So they're about, so pixels are effectively 15 degrees in diameter in these maps. So I think reconstructions of co-rotating material have been managed to obtain reasonably okay with as few as even 10, 20 measurements from IceCat. If you've got about 30 odd measurements in a single day, then you can reconstruct things a bit better. IC instruments takes 100 or more measurements per day, I think, and that's what goes into these plots. Even more data are typically available from UTI, where they can get up to 1,000 or more observations in a single day. And when you get up to that kind of level, and if you are very strict about the quality of the data that you let in, to really exclude data which are definitely poor quality, or the results the results questionable, then if you do that with that kind of number of observations, you can end up with this kind of reconstruction in the ecliptic plane, with velocity on the right, density on the left. And with this, you could see CMEs merging together, all sorts of material there. They're really, really beautiful movies, but this was many observations per day and several months of very careful analysis to make sure that only decent data were going in, and increasing the resolution of the tomography. But it represents what can be achieved and what we would love to be able to achieve on a regular basis. But we're quite a long way from doing that. LOFAR data, I think, having experimented for a few years now, I think really the sensitivity of the international stations, although good, is not necessarily good enough to do many more than 30, 40, 50 observations in a single day. So I think with the LOFAR data, we are actually better placed to focus on longer duration observations and extracting more information from single points and single lines of sight than we are with trying to chase down doing too much of the tomography. But it is absolutely fabulous what can be achieved. Okay, sorry, brief diversion into nice pretty picture land, and then we come back to this formula here. Okay, so we've got the spatial spectrum of the density variations there, which I've been describing. So we can get this axial ratio and things like that. We can potentially model from the power spectrum, and then we've got the elephant, the source visibility function, and it's about time we at least acknowledge the existence of the elephant. So apologies to non-British and Irish speakers there. So we're going to address the source visibility function and take a look, not take a look at it, but at least illustrate its effect. So now we're verging into techniques which those of you who are radio astronomers might find a little bit more familiar, but only slightly. You may be familiar with the concept of the UV plots in radio astronomy. And I'm doing something vaguely similar here with the IPS data. So say we have a pair of stations. We have a cross-correlation function between them. That cross-correlation function has a peak value. And it has a peak value. It also has a value at 0 time lag. So say we take that cross-correlation function, those 0 lag correlation values and those peak correlation values, and we place them on a UV type plot. But instead of the X and Y axes being U and V coordinates, they are instead radial baseline versus tangential baseline, which is just the perpendicular component to the radial direction. And then we say, okay, so we have this pair of stations with this baseline 1, which is going in this direction in the radial tangential plane. So at either end of it, either end of this baseline, we place the value 1 of either the peak of the cross correlation function between them, or of the zero lag value, cross correlation value between them. We take our next pair of stations. We have different cross correlation function, different baseline, and do the same again. And we gradually start to fill up this plot with different points, which you end up with a symmetrical pattern. And this is what we end up with. So in the top row is all the zero lag correlation values for all the pairs of stations for this CME observation of the September 2017. So before the CME really started to take hold in the data, what we see is this nice little slightly elongated elliptical pattern here. Now that elliptical pattern is basically illustrating two things. It's illustrating, as a first approximation, the shape of the average shape of the density variations themselves. So we could say, okay, it's elongated, and it's elongated approximately in the radial direction. So it has an axial ratio. So we can measure from this plot the axial ratio that we could then use in our modeling. The issue is that the radio source itself has a broadly similar shape. So this, if I take a look at a source map of 150 megahertz for 3C147, would also be roughly the shape of the radio source itself. So the fact that this is not elongated exactly in the radial direction, but it's offset from that, and possibly a part of that elongation itself, may well be a reflection of the structure of the radio source and not so much the structure of the medium. So we've got the convolution of the two in these plots, which is why we need to suddenly start addressing this elephant, start addressing the idea of source structure, and start incorporating it properly in our modeling. But what's interesting about these data is what happens when the CME hits. This pattern, which was broadly consistent and broadly like this for several hours before the CME happened, suddenly changes, and it changes quite dramatically. You can see that it becomes longer. It becomes more inclined to the radial direction. It even starts to take on a little bit of a spiral shape. It flips sides. So if we're making the assumption, which we typically do, and it's a reasonable one, that the density variations are elongated, and they're elongated in the direction of the magnetic field, then what this is reflecting is effectively a change in the direction of the magnetic field as the CME passes across the line of sight. So effectively, we're starting to look at a reflection of the magnetic structure of the CME, because the radio source is not going to suddenly change its orientation over the space of a few hours, just coincident with the CME passing across the line of sight.
Richard,
so,
can I ask you a question?
Yeah.
That's very interesting. That you said this, one of them even takes on a spiral structure. Is that an indication of even more complex patterns in the magnetic field that you could possibly get out of the data?
Yeah, it's a reflection of the extension of the line of sight.
Okay.
So we're looking at an extended line of sight, an extended structure crossing the line of sight. So so it's not only this CME, it's not only the CME at one point, it's the average of a line of sight through a CME structure, and combined with what's happening in the solar wind surrounding it.
I see. Okay. Thanks.
I mean, we do need really proper full modeling to be able to get to say something definite. But I think what I can say something definitely is that we're, or as certain as I can be, that we're looking at rotation of the magnetic structure.
Yeah, that's my first thought when I see it. But yeah.
And obviously from this, we're only looking at alignments. We can't tell whether it's north or south. But the fact that we can see a change in that alignment is itself something that we've never before been able to see in IPS, because we never before had an instrument like LOFAR.
And do you know if it's compatible or with the idea of like a flux rope that you're seeing through different lines of sight through a flux rope with time, I guess?
That's a possibility. It's difficult. It's difficult to say. I think we need the full MHD modeling to take a look at it, what we're looking at. I haven't started taking a look at any kind of modeling as to what we might expect to see given particular scenarios with regard to a CME. Okay, so that's what's happening with the zero lag correlation, because the zero lag correlation, then this pattern, that is basically the convolution of the spatial spectrum of the density variations themselves, the spatial, well, rather than the spatial correlation of the density structure itself, combined with the structure, the spatial structure of the radio source that we're looking at. So that's what's particularly intriguing about that. Now, if we do the same with the peak correlations, we end up with a slightly different view. We end up with this very elongated structure, which is broadly radial in direction, very slightly offset from radial, perhaps, but broadly radial in direction. And as the CME passes across the line of sight, it remains broadly radial in direction, perhaps some slight variation, but mostly pretty much radial in direction. So what we're looking at here is most likely the reflection of the velocity vector itself. So whereas with the zero lag correlations, we're looking at the vector of the density structure. With the peak correlations, we're looking at the vector of the velocity structure. So we're seeing then that the velocity is likely to be remaining mostly radial in direction as we expect. And it's the density structure which is changing in response to the changing magnetic field passing across the line of sight. So suddenly, for the first time, we're basically able to separate these two vectors, which is something that we've never really been able to do before with IPS. So this is quite exciting stuff. As usual, I'll still need to write it up in a paper, but we'll get there. So one final thing now, and that's just to take a look at the scintillation pattern itself moving across the array. That's all it is. So taking all the stations that we measured with this particular observation, all the international stations, you can see the cluster of the Dutch array in the middle here. You got the Polish stations off to the left over here, UK and Ireland off to the right. Each of these dots is simply colored by the intensity received at time, with time. So what we're effectively looking at here is basically just the blobs of the scintillation pattern itself flowing across the entirety of the LOFAR array. And you can see it's quite blobby structure. I mean, it's fairly sparsely sampled, certainly, but it's pretty blobby structure, as we might expect. And with these blobs moving around and squishing and squashing in slightly different directions, but all broadly moving in the radial direction away from the sun, as we expect. And I just show this because it's a pretty picture, and that is it.
Can I ask a question about the pretty picture?
Yeah,
That's really cool, Richard. I'm just looking at the time scale there. These are, you can see it changes on time scales of seconds. And I assume that's too quick. I assume for, say, ionospheric variation of scintillation. This is actually from the heliosphere, yeah?
This is the heliosphere.
Yeah.
Yeah, if you're looking at the ionosphere, then you see you see this variation happening across the LOFAR core.
And on what time scales do you see the ionospheric variation?
Ionospheric stuff, then that's predominantly tens of seconds rather than seconds. I mean here this is interplanetary. It's stuff traveling at several hundred kilometers per second, so it's only taking a few seconds to go from one side of the array to the other.
That's amazing. Really cool.
Yeah, we do have similar movies for the ionosphere as well, just across the core, and then you see the scintillation pattern is much more elongated, and it's just moving in waves across the core, typically from northwest to southeast, or from northeast to southwest.
Yeah.
But yeah, you're effectively looking at the turbulent pattern of the CME moving across the field of view. And so I'm looking very much forwards to having this picture filled in a little bit more with another station, which I guess would be somewhere up towards the top of the screen on this plot. It'd be quite nice now. In a few years' time, and there should be one in Italy coming next year. So that will also be towards the top of this plot, I think.
I was about to ask, yeah. So your interpolation map doesn't go as far as some of the outer points.
No,
that's just the interpolation algorithm, or
I guess so. This is just using standard contouring stuff from Python.
Yeah.
Great movie.
Anyway, that's basically it, folks. So I'll happily take any further questions or points you wish to discuss in the remaining time, as you wish.
I just have probably a really, really silly one, Richard. You see that point pretty much in the middle of the moving blobs?
Sorry, the
data point in the middle of all the moving blobs. It seems to say the same color for pretty much the entirety of the movie.
That's probably just rubbish data, which I've
fair enough.
Which is still in there.
I have a question. So you mentioned that maybe LOFAR's niche area would be looking at single lines of sight rather than trying to do the tomography type of things. Is that because of the sensitivity of LOFAR in the high frequency bands is not good enough, or the collecting area, or what's
yeah. I mean the sensitivity of the IC instrument in Japan, which is it's a transit instrument, but it's a very sensitive one, and the sensitivity of the UTI telescope, which can track, but the sensitivity of that for IPS is much greater than the individual sensitivity of an international station. So so whilst the collective sensitivity of LOFAR itself and the collective sensitivity of the combined core is excellent, that of single international stations, when you're taking samples at 1/100th of a second, or even 1/10th of a second, is still not as good for being able to detect very many weaker sources. And if we want numbers of sources, we need to be able to detect weaker sources and not just the stronger ones. So that's basically what I found. Whereas UTI will get down to very easily to sub-Jansky level with a single station. With a single international station at these integration times, I hesitate to go below a Jansky, and prefer to stay quite a bit above that, in fact.
Okay, yeah, that makes sense. Any other questions from the audience? Now is your time. We're lucky to have Richard here.
Maybe I have a question about the solar radio bursts, and do they mess up these observations? Because at the same time as the CME, you may have flares. I guess the flare would be much earlier than the CME in its propagation, but another one could occur if the sun is particularly active, and I guess you couldn't do this then.
Yeah. Solar flares complicate matters.
Always.
Always. So yeah, if there's a strong solar flare and the sun is visible in a side lobe, then our data are corrupted quite significantly by the solar flare itself. With the high band array tiles, the HBA tiles of LOFAR, they have quite a strong grating response, and the HBA system as a whole has quite a strong grating response. And that means that if the sun falls in a null point, then it barely contributes at all to the signal. Now we can make use of that to some extent. What that generally means is that different stations will end up sampling different portions of the solar radio burst, with other parts of the band being mostly clear of the radio burst, and we can see the IPS. But the HBA stations are all oriented differently to one another, which means that the grating lobes point in different directions, depending on different stations. And so, whereas one station we might be able to say, okay, 150 to 170 megahertz, we're good, we can use that part of the band. In another part of in another station, that might be covering very well, being obscured by the solar radio burst, and a different part of the band is relatively clear of it. So yeah, it does cause a bit of a problem.
Yeah.
If no one else has a question, I'll ask another one. I'm just moderating, but in terms of the data analysis, like obviously radio imaging is exceptionally compute intensive. This sort of IPS observations, is it similarly computationally intensive or a lot lower? Much less?
No, it's a lot lower. We're looking at beamform data.
Okay, so it's already done.
So basically it's dynamic spectra.
Yeah, okay, gotcha.
And when I'm talking about cross-correlation, I'm talking about cross-correlation of time series, intensity time series between stations, not cross-correlate, not visibilities.
Okay.
Yeah, so it's basically, so a 1D problem kind of thing. And is the calibration of each international LOFAR station then, I guess you really need, do you need good calibration between the stations, or can you kind of normalize?
Depends what you mean by calibration at this point.
I suppose, I guess, in terms of the received intensity or measured intensity, if that makes sense.
Yeah. We need the stations to be as well calibrated themselves as they can be, because if the calibration is out, your beam width is wider, your sensitivity is lower. So effectively, if you took your station and successively changed the calibration table to be pretty poor to being pretty good, what you would effectively see would be a tightening up and a focusing of the beam pattern. So you want that calibration to be as good as it can be. But in terms of calibration of timing between different stations, that is less important for this. I mean, the geometrical delay between stations is of the order of what, milliseconds at most, whereas we're looking at stuff that's crossing our line of sight in seconds. So if we're a couple of milliseconds out, it doesn't make any difference to us.
Mm.
The timing calibration between stations, we are less concerned about. We can treat each station as being effectively independent.
Okay, great, thanks. I think there's a question from Beijing.
Hello, Richard.
Hi, Beijing.
Yeah, hi. I was still thinking about the previous figure you showed, because it aligns so well as a line. You should off x about 25 degrees, and the velocity, no, the time lag aligns as a perfect line. Is that? I'm still thinking why it aligns so well at previous.
Right.
Yeah.
I mean, indeed, I didn't quite explain that. So in that initial plot, when I was looking at one of these of baseline versus time lag, and you saw that if I assumed the solar wind flow to be 24 degrees off radial, that the fit became better. That's actually because of this. So effectively, that's providing the better fit along this alignment.
Okay.
Which is actually incorrect in terms of the velocity. But for whatever reason, instead of the fit being better in the radial direction, as you would expect from the lower plots here, it's actually matching. The time lags are actually matching this direction.
Yes.
So that direction then is not necessarily the velocity vector, but it may well be the magnetic field vector.
Oh, right.
We need to model. Yeah. We need to model properly, but it's why effectively as an IPS community we've always assumed radial direction, and we've almost fixed things to be that, because we know if we allow it to vary, it's not going to pick up the velocity vector, but the magnetic vector.
Yeah, I was expecting the velocity to be a distribution.
Yeah, it is a distribution. Indeed, it's a distribution. Indeed, it's a distribution, but it's focused on the radial direction.
Oh yeah, it's focused on the radial direction. Okay, thank you.